as my sort of role within Intel, what I do is really work with enterprises, partners, OEMs, SIs, whatever, and really try to understand what our partners and customers are trying to do with AI, right? So, one of the things that we realized is this is still very, very early for sort of the AI revolution or evolution. And what we are really curious about, so that we can drive sort of the ecosystem and partnerships, is really understanding what folks are doing with AI, right? So I want to sort of go into that a little bit as part of this presentation. So let me get started. So first, the business imperative. There is an explosion of data. We all know this. The automotive industry, the manufacturing industry, they're just, the creation of data and the collection of data is tremendous, right? Now the challenge though is, what are we doing with it, right? So the data is there, right? And what we are really trying to push on the innovation side is what can we possibly do to sort of make better prediction or do better analytics on the data that we have and are collecting, right? So what I wanted to do here was talk a little bit about how I see AI fitting into sort of the overall evolution of analytics, right? So if you think about sort of traditionally what enterprises have done with analytics is it tended to be very sort of backward looking, right? So it's like, okay, well, we have all this data, something went wrong, right? And we want to find out why something went wrong, right? So it's always sort of a retrospective look at the data to understand what went wrong, and so potentially in the future to avoid it. Now, what you're seeing more recently, though, in the last couple of years, is we have enough data and enough compute to sort of look into the future, right? So given what we are seeing, right, what is the possibility, what is the probability that something can go wrong, right? Either positive or negative, right? So it could be even a positive event. So it's starting to become much more sort of predictive in its nature, right? And eventually what we want to do is not only predict what will happen, but also teach these systems to take corrective action. So it's almost like as a decision model, right? So I know this is going to happen, and I want to fix it before it happens, so I'm going to sort of build AI systems that can actually sort of automatically take corrective action. And that's what I see as sort of the top right of this, right? So the cognitive analytics is where sort of the world is going into. So this is sort of an interesting analogy, and this is where AI is really pushing that sort of evolution in what you see here towards more predictive and more sort of cognitive aspects of analytics. Right? 3 years ago, there were very specific industries that were looking at AI. So finance, for example, at least globally, right? So finance, automotive, and healthcare, I would see were the sort of more innovative early adopters of AI. Right? Now today, it's all over the place, right? So everything from consumer electronics to healthcare to retail. Obviously, a lot of governments are investing heavily into AI. There's industrial transportation. Transportation and finance, I think, is still sort of at the leading edge of this, but today I can walk into pretty much any industry, any company, and say, they are investing heavily in the AI space. So it's no longer just a fad. It's actually, solving very specific, very concrete use cases that we'll actually talk about later on in this presentation. Right. Now, having said that, though, right? So this is similar again to the data that was presented earlier. Everybody's looking at it, right? But if you look at real adoption, it's still very, very early, right? So I'll give you an example. So I was talking to the infrastructure folks and the data science folks at a very large sort of global bank, right? And they did a poll across their entire organization and said, hey, what are the use cases that would be applicable to for AI? So what are the use cases that we want to go after with AI? And what they got back, I mean, they thought we'll get maybe 10, 15. They got 150 different use cases back from that poll, right? And they were like, okay, well, where do we start, right? So they said, okay, well, let's start prioritizing these. Let's pick 2 or 3, and let's figure out, well, how do we build these systems? So that's the potential. That's where everybody's at right now, right? So they know there's value, right? They're starting to invest in 2 or 3 like really important sort of high priority use cases, but the potential for long-term growth is tremendous, right? So this is just still very, very early. It's there's a huge growth potential with respect to where we can go with AI, right? And that we have seen that across the board, right? It's not just financial services, it's not healthcare, it's pretty much every industry that you can touch potentially, right? Now, what I wanted to do again, very quickly, right, set a baseline for how we define AI within Intel, and I think this is broadly sort of an acceptable definition, right? So, there are actually several variants of what we call AI, right? So AI is a very broad term, right? So there's things like reasoning systems, there's things like traditional machine learning approaches, there's deep learning, there's actually many more, but essentially there are different approaches that you can apply to different types of problems, right? And I'll go into a couple of this. So let's talk about machine learning versus deep learning, right? So this is important, and I'll spend a few minutes here. Let's say you're building an app to detect and identify faces, right? So the goal is, okay, every person in the audience, as soon as you walk in, we have a camera, we don't, but just assume that we have a camera, and as you walk in, we can automatically register you by just looking at an image or a video capture of your face. So that's the system that you're trying to build, right? Now, in a traditional machine learning approach, what you would do is you would define the features that are important to identify one person from the next. So what are those features? Those are things like distance between the pupils, or width of the mouth, or length of the nose. So these are features that you have to design algorithms to actually detect and measure, and then make the distinction between faces, right? So that's, at a very high level, that's how I would define sort of traditional machine learning approach to doing that, right? Now, what is deep learning, right? So here, what you're doing is you're automating the definition of these features. So what you do, just to be very specific, if you're using supervised learning, we take each person's face and we say, well, this is person A, this is person B, and we train the system to automatically identify what features are important and what features are not important in making that distinction. So the deep learning neural network actually says, oh, I see that the distance between the pupils is different. So I'm going to use that as a feature to distinguish. And so it learns these features automatically, right? So if you just think about that intuitively, building really, really complex systems is much easier using deep learning than sort of traditional machine learning approach, especially when you have thousands of features. Not only that, but you're also detecting features that maybe even humans may potentially miss while designing these traditional algorithms. Right, so here's where the power of so the more advanced type of AI comes in. So, and if you look at this process, right, so at a very high level, I would split it between a training and an inference. So that initial detection of features is what I call training, right? And the inference is where now you give it a new image, right? And it's automatically able to tag that person as person A. So from a sort of process perspective, you have training, where you're training the system, and then you're doing inference, where you're actually doing the prediction or doing the tagging automatically. So that's how you would look at it. Now, the key here is that the more data you have, the more accurate your models become. Because you're giving it more samples of data, it's able to identify more features, and the more accurate these models become. And training becomes a lot more, inference becomes a lot more accurate, right? Now, what is Intel doing here, right? So this is where it gets really interesting. So what, at a very high level, what we realize is that, the compute is really, really important, right? So as you're training these systems and as you're doing inference, what you want to be able to do is very easily deploy on existing infrastructure. And that's where the power of the Zeon platform comes in, because most companies, most enterprises out there have large Zeon deployments. Not all of them are 100% utilized, right? So they're actually running different types of workloads. Now, for an enterprise to start exploring AI, and even in some cases deploying AI at scale, what you want to do is maximize the ROI. So the Zeon infrastructure is actually a great way to start and eventually even deploy some of these models at scale, right? The other thing is, beyond Zeon, we are also building a pretty extensive portfolio of hardware products, everything from the data center to the edge, right? So this is not only training, but you want to do inference on a drone, for example, or on a car, or even on a camera, right? So in a security camera. So what we are doing is actually building the hardware and the software platforms to support training in the data center, inference in the data center, inference on the edge, and I'll talk a little bit about that. But it's a really, really broad portfolio of hardware products that we are bringing to bear to solve AI problems, right? The third thing, again, was touched upon earlier, is we really rely on our ecosystem partners to bring these solutions to life, right? So, yes, at Intel, we are really good at building hardware. We build great software. We even have our own data scientists and folks who can work on these real-world problems. But that's where we don't have the scale that our SIs bring to the table when it comes to actual sort of solving customer problems using AI, right? So that's where you guys come in, where you build end-to-end sort of algorithms and deployments that actually solve real customer use cases. So what we're really trying to do is expand these partnerships where we can partner with you to solve, and we'll obviously provide that expertise in the back end, but what we are really trying to do is equip our partners to go off and solve these problems. And this is where we really want to invest in sort of the ecosystem partners to help do that. And finally, one of the things that we are good at Intel is just driving research, right? So, we have Intel Labs, we have Intel AI Labs, both here in India and globally as well, that are investing in new techniques that push the edge with respect to, AI algorithms, AI hardware, and that's something that we are really, really investing in. So, very broadly, these are sort of our 4 pillars, if you will, with respect to AI investments. All right, so let's talk about the stack a little bit. So, traditionally, Intel has been known as a silicon company, right? That hasn't been true for a really, really long time. So, yes, we build silicon. We are really good at building silicon. But as you can see, the investment is much more than that, right? So we have libraries that optimize AI deep learning workloads on Xeon architecture. We have optimized frameworks that have been specifically optimized for Xeon and other Intel architectures. We have tools that make development of these models much easier. So the time to market is important. It's not just it's not about the silicon itself, but how can we make the development of these solutions faster and easier, right? And that's where we are investing in these tools and platforms. And I'll talk a little bit more about them in detail. So let's start on the left here, right? So the Intel Deep Learning Studio, right? So if you think back to what I was saying earlier, right? So you have data, right? You have to take that data, build a model, a neural network model. You then have to train that model using that training data set, right? Once you train the model, you deploy the model, and then you do inference. So that's sort of a very high level, I'm simplifying tremendously, but that's a very high level pipeline or a workflow, if you will, for deep learning. Now, the faster you do that, right, the faster you get these solutions to market. And it's not just about training time, it's about how quickly can you label the data? How quickly can you iterate between models where you find the optimal sort of architecture that solves a specific problem? So we are building all these tools that actually make this process much faster and much easier, and that's what the Intel Deep Learning Studio is, right? And then the stuff on the right is more geared towards deploying those trained models on different architectures or hardware platforms, right? So the deep learning toolkit, you can sort of build inference models very quickly. The computer vision SDK is used for computer vision specific optimizations for CPUs, GPUs, whatever have you. And then the Movidius SDK is more, again, targeted towards vision applications and optimizing inference for vision. So these are tools that simplify that workflow, starting from a very high level sort of model development and training all the way down to optimized inference for different hardware targets, right? BigDL is something that we've developed within Intel as well that's gained tremendous traction recently. So this is for deep learning and AI deployment on sort of existing Hadoop and Spark architectures, right? So you'll see that a lot of your customers already have a big data infrastructure. They have some sort of Spark deployment. And if you want to sort of introduce AI into that existing ecosystem, BigDL is a very easy way to do that. right? So depending on where how mature your customers are, there are different software packages and tools that we're building that will sort of make that easier for you to adopt, right? Now, if you go to sort of the libraries, right, so this is going beyond just the tools and the frameworks, we've optimized math libraries to take advantage of the Zeon architecture to make some of these workloads run much faster on Zeon and some of the other Intel architectures, right? So MKLDNN, DAL, for example, these are all optimized math libraries that make deep learning frameworks run faster on Xeon, right? So what this helps you do, what this helps us do is optimize things like TensorFlow or Caffe or Torch to run more effectively and more faster on sort of Intel architecture. Now, the one on the right, I think it's a little bit interesting. So what we are also trying to do is make this as easy as possible. So the Nirvana graph is actually one that we've developed internally and it's still in beta, but what we're doing is taking these different frameworks, right, and making it as easy as possible to develop a model once and then run it across different hardware targets. So you can say, let's say, build a model using TensorFlow, right? You can then run it on Xeon for training, but you can also very seamlessly, if you wanted to also use CPUs or GPUs or FPGAs, you can then easily, without making any changes to the model or without worrying about sort of lower level optimizations, use this intermediary Nirvana graph to easily deploy across different targets, right? So it actually makes your deployment much, much easier using ngraph. Now let's talk about the hardware. So again, so the way we look at this is very, there's two components. There's training and inference. There's also data center versus edge and gateway, right? So if you are looking at traditional machine learning, right? So the stuff on the left, you can do this very easily on Xeon, right? If you wanted to run sort of lower power, low latency applications, FPGAs are perfect for these types of applications as well. Now, if you want to go into deep learning, again, Xeon is sort of our core product here, right? So you can do this for training in the data center. You can use it for inference on the edge as well, depending on what those applications are. Now, for most workloads, the Xeon does really, really well, right? If you are looking at more advanced applications where you need higher bandwidth and higher performance, we are actually building accelerators for the data center called the NNP, which speeds up training beyond what the CPU is able to do. Now, for most applications, you may not need an NNP, but for really high bandwidth applications, let's say you're working with high bandwidth audio, video, high resolution images, for example, you may need the acceleration, right, in the data center. So that's something that we are building today that is in private beta with a few customers, but will be more widely available next year, right? So this is the NNP. Now, for inference in the data center, that's something that you can use as well. You can also use the FPGA that you see on the right, right? So again, for low latency applications, right? So some financial models, for example, have a very low tolerance for latency, and in those kinds of cases, you can apply the FPGA as well. And then when you get to the edge, right, there's a much broader portfolio of products. So depending on what your application is, you can use the Iris graphics accelerator, you can use the Movidius platform. We have the GNA, which is specifically for sort of audio and speech. Mobileye is another big component of Intel's portfolio that's targeted specifically for autonomous driving. And finally, you can also use FPGAs. So depending upon the latency, depending upon the power requirements, depending on the application, we actually have a very broad portfolio of products that you can apply to the inference part of this on the edge. Right? Now let's talk about a little bit about the application. So in AI specifically, it's really the way we look at the problem is based on the type of data you're trying to process, right? So it's not necessarily industry specific. It's more about, well, what data and what applications are you really trying to drive using AI, right? So is it a time series data? Is it documents, it's natural language processing, it's the tabular data. We've done a lot of work in speech and sort of audio type of applications. We've done some work in video activity detection, and also the one that you already saw with respect to image processing. So I think the type of data is where the sort of the models or the neural networks actually differ. So the types of data that you use for, the types of models you use for image classification, for example, are very similar irrespective of what industry vertical you're targeting, whether it's medical diagnosis or you're doing aerial imaging or whatever, right? So the models are very similar. The only difference is obviously you'll use different data sets to train your models to do different types of feature detection depending on what application you're building. All right, so let's talk about a few. So the first one, this is actually really interesting. We did this work with a large medical devices company in the US, right? And what they wanted to do was they wanted to automatically detect brain tumors in these large 3D images, right? And large 3D images is the key word here. These images are like extremely large, right? And they explored GPUs in the past, and the problem is the memory architecture that GPUs have were not ideal for the type of application they were trying to develop because of the size of these images, right? And it turns out that the Zeon actually has a very much more powerful sort of memory architecture that actually supported deep learning applications with these types of images really, really well, right? So what we did, so traditionally what you would have to do is you would take this large image and you would segment them into smaller parts, right? Which is a very tedious process. You were not able to train as fast. And so what we did was we worked with this company and we said, okay, well, we've got a few data scientists, let's help you out. And we were actually able to speed up the training process significantly thanks to the Zeon architecture. And it came down from hours to minutes with respect to the training time, right? So what this model really does is it takes these 3D images and automatically detects tumors, right? With a very high degree of accuracy. So what this is meant to do is be sort of aid to doctors so that they don't have to focus on too many images and they can focus on sort of few key ones, right? Really, really powerful use case. Here's another one, right? So there's a lot of healthcare stuff just because they were one of the industry, in a sense, was a really good fit for some of the models that we were building. So here's another one which was sort of around genetic prediction. So what we were trying to do here is take genetic samples and identify the probability that somebody would develop cardiovascular disease based on their genetic signature, right? Very different from the previous use case. So images is, everybody understands, it's an easy one to solve for the most part, but this is a really, really interesting use case. This is, mostly tabular data. It's not, a traditional sort of image use case. It's a very complex model, and we were actually able to build one that was about 85% accurate, which is actually really, really impressive, right? So taking genetic samples and specifically looking at cardiovascular. Now, you can easily take this model and deploy it to other types of disease as well, right? As long as there's a correlation between the genetic markup and that specific disease. Right. Here's another one. This is also genomics related, but what we did here was build a model that would automatically understand or automatically define the protein function, right? So you have a series of amino acids, and what we want to do is just based on the amino acids, can we very clearly identify what the protein function of each of those would be, right? So again, it's a very, very specific use case, but again, really, really powerful. So you can see the breadth of some of these things. Even within healthcare, I think most people sort of gravitate toward imaging, but there's a lot of stuff within healthcare that is really relevant for deep learning types of approaches. Right. So let's switch gears a little bit. So this is actually around natural language processing. It's a really, really interesting use case. So we were approached by a really large financial services company, And it was essentially an investment bank, right? And they have analysts who are reading thousands of documents every year, right? So if you're an analyst for the automotive space, you're reading about all the major automotive manufacturers in the world, you're understanding competition, you're understanding price, customer behavior. And so the job of these analysts is to really understand their market really well, right? And what do they do with that information? They advise clients, they predict, they rate stock, for example, so that's their job, right? Now, what if we built a system, right, that was like a Q&A system? So you go in and you say, hey, tell me about the automotive landscape in India, right? Or tell me about the competitive landscape of financial services in Europe, right? Now, that's a really, really complex question, right? It may be easy for us to process, but for a computer to take that and say, well, what kind of documents should I surface to the person asking this question, right? So that's the key. So instead of reading 1,000 documents, can I focus this person on only 5 documents so that they can, instead of reading for 100 hours, maybe in a couple of hours, get up to speed on that specific space. Now, traditionally, how would you do that? You would say, okay, automotive, India, competition, and you would take those words and you would do a keyword search, right? That's fine, except it's not very effective, right? What you really want to do is build an intelligent system that takes that complex question or that complex query and understands the question in a form that humans do, like how humans do. So what does competition mean? Does it mean price? Does it mean how many players are out there? So what are the related words to competition that may be relevant in that search, right? Automotive, is that cars? Is that trucks, right? So what we did was we built this really complex sort of multi-dimensional map of keywords using deep learning. So we took a bunch of documents that were publicly available, and we said, okay, what is the correlation between the occurrence of a word and the occurrence of other words within that context? And so really understanding the language using AI and deep learning. So when you ask a question like that, it's not only focusing on those words, but also understanding the concept where it's able to sort of, answer it in a very interactive way by raising the documents that are relevant, right? So documents, sentences, paragraphs that are relevant to answering that question. So what we're doing is really shortening the time it takes to learn something new, right? Again, very interesting. So what you can do with this, if you think about this broadly, you can apply this to the medical space, right? Doctors' notes. Doctors write, hundreds of lines of notes every day. Can you build a similar type of system where if a doctor types in a symptom, they're able to sort of surface all the relevant patients that had similar things or things that were related? So the application of something like this is actually much broader than what we had built it for, right? Here's one in financial services. Again, this is time series data. So again, let's think about, the problem that we were trying to solve here was to take a stock market, let's say, time series, right? So stock X had this specific movement over the last 1 week, right? Now, we know that happened last week, right? So now can we predict with a certain level of accuracy what's going to happen next week, right? Now that question is very valuable, right? If I could answer that with a high degree of accuracy, I wouldn't be standing up here, right? It's a very complex problem, and you can make a lot of money if you were able to predict. Now that's a very complex question, but yes, let's start with how you would start to solve that problem, right? So if I found a pattern that happened last week, can I look at historic, the historic stock market data to find similar patterns, right? And then as a next step, once I find similar patterns, can I then correlate what happened after those patterns to what I'm seeing today, right? So this is a multi-stage problem, right? You still may not be able to, things can happen for different reasons, but this is one way to solve this problem. So what we did was we built a deep learning-based model that took a sample, any sample that you gave it, right, and found similar patterns, not exactly the same. So it's easy to find the exact same thing, but because it's just it's a search, it's a simple search. But can you find patterns that were in some form or the other similar, right, to what you're seeing now? And that's a very interesting problem that you can solve with AI. So that was the first step. Now, once you do that, can you then start to predict, based on what you saw in the past, to what will happen with this specific stock? We're actually building a model to do that as well. Again, it's not a solved problem. It's very much in the research phase. But these are the types of questions that we get from our partners. Is can we use this data to make interesting predictions around stock market behavior is one that we see very, very often. Right? This is a great one as well. So, this is an interesting image. So this is actually an offshore oil rig, right? So this is a very large oil exploration company, and they built these offshore oil rigs, obviously. And this is the submerged part of it. It's not above the water, it's below the water. Now, so what's the problem here is corrosion. Corrosion is a huge problem. And it's not only a problem here, it's a problem with pretty much any sort of large-scale industrial deployment. So wind turbines, solar panels, offshore oil rigs, right? Corrosion is a big problem. And they spend millions of dollars trying to detect corrosion early enough where they can prevent structural failure. So you got to catch it early enough where you can do the, what's really interesting here is also it's submerged, so it's not easy. So they have these automated, remote controlled submarines. They're underwater drones essentially, and they capture these images, right? Then after they capture it, they transfer it up to the control station, if you will. Then a human sits there and looks at every frame, right, trying to detect, and then manually draws a box around it and says, oh, there's corrosion. So you'll see this here, right? So there's the one that's a red box is actually highly corroded, whereas the one that's green is sort of, all blue. I can't tell what that is, but the blue one is less corroded, right? So they're manually making this decision, and then once they've done that, then they have to send a human down there, right, and manually sort of change this, right? Now, what if you could do this in real time? Right? So what if you could build a drone or an underwater submerged vehicle that had a robotic arm, and as soon as it saw the corrosion, the arm came out, pulled the screw out or the bolt out, put a new one in there, right? So how much money, how much time would this company save, right? It's a huge value add, right? The problem is the automated system. So here what we did was we built a deep learning model or an AI model that automatically, it's a multi-stage problem. You have to detect the bolt, so you have to say, oh, there's a bolt. Second, you have to classify the bolt, right? So is it corroded or not? And then you have to decide, well, how much is it corrosion? Is it 90% corroded? Is it 20% corroded, right? So we worked with this company to sort of collect this data, built a model, we trained the model, and they're in the process of actually deploying this for the first part of this, just the detection part, right? But in the future, you can see where this is going. This is actually headed to sort of an automated maintenance sort of model where you can maybe potentially train the model in the data center, but do the inference on the edge, so on the drone itself. So it can take corrective action in real time. So we are seeing a lot of this kind of stuff, and it's applicable not only in oil and gas, but manufacturing, manufacturing plants also, right? So if you have a conveyor belt and you have a production line, you want to identify defects in real time, and you want to take corrective action. It's a very, very similar type of model. So again, a lot of applications. And so there's many more, right? So we are seeing a lot in sort of autonomous driving as well. But how do you sort of get started with Intel? So this is the key here, right? So you want to go out and solve these problems, but you also want to understand Intel's technology and help us help you, right? So that's the key here is, like, we are building great silicon products, we are building all these tools, but what we also want to do is educate our partners so that you can get familiar with these tools and what sort of applications that our hardware and software stacks are optimized for, and go build these solutions yourself. So we have several initiatives on the way that, one of the things I'll talk about on the next slide, but there's a lot of resources online that you can start with. So you can start educating yourselves on the software. You can get familiar with our sort of natively optimized frameworks like TensorFlow, Cafe, Torch, Neon, for example. There's a lot of courseware. And there's also a lot of use cases and case studies that we share publicly on this site, right? So it's, some of these things are easy to replicate. Once you solve them once for one client, it's very easy to sort of take that model and apply it to a very different domain, but a similar type of problem, right? So imaging diagnostics in healthcare, you could potentially use the same model for, let's say, detecting defects in manufacturing plants, right? So, we want to sort of publish these use cases, publish the solutions so that you can go out and actually scale this across multiple customers. And that's what we're trying to do with this portal here. The other thing I wanted to sort of quickly highlight here, so this is actually launching next month. We are also building an AI partner program. And this is more hands-on, right? So what we want to do is really onboard a select set of partners, whether they're OEMs, ISVs, SIs, that are focused on solving very specific industry vertical problems, right? So you may be an SI or an ISV that's focused only on financial services, right? So we want to sort of, work with you folks to really enable you, arm you with the right tools, educate you on the Intel platforms, on the Intel software, do co-marketing where it's possible, and also do matchmaking, right? So if we see customers come to us directly and say, hey, this is a problem. We may not have the scale to go off and deploy 10 data scientists on each of these problems, but we have partners who can, right? And so that sort of matchmaking is something that we want to do as well. So this is something that we are launching in late April. It's not live yet. I know somebody on my team is actually working on putting this together. So we'll be launching this at an event globally in the next month or so. So, keep an eye out for this. That's all I had. Thank you.